All right, let's get started here with the notes on the energy basics. This is part 2 in our series. Let's talk a little bit about energy. Energy is the ability to do work. And when I look at this light bulb, I'm noticing the work that energy is doing. It's lighting it up. And if I touched that, lighting up that light bulb, and if I touched the light bulb, it would probably feel hot. The first law of thermodynamics is all about the quantity of energy. It always stays the same. One cannot create or destroy energy. You can only transform it. And so the electricity, the electrical energy that's lighting up this light had to come from somewhere, and it came from the sun. Millions of years ago, the sun shined its photons down onto the earth, and it excited chemicals within plants, and those chemicals in the plants made sugars, and through a process called photosynthesis. However, they died, and over time what happened is earth started to cover them up. Great pressure and time created coal. So think about already all of the different energy that has been converted and transformed so far in our process. And what humans have done is they've built up and dug up the coal and then burned it into coal-fired power plants, which are, the coal is burned, and that heat energy is used to boil water, which creates steam, and the steam turns a turbine, and that creates electricity, right, as the turbine and generators move. And then electricity travels along power lines, and it finally gets to our light bulb, right? There's my little wire there, and the electrons that move at the speed of light along that wire enter into our light bulb and travel up through these very thin filaments, and those filaments have a little resistance to the electrons, and so the electrons heat up, produces a lot of thermal energy as this happens, right, along with light. And the electrons do that, they exit the light bulb and move on their merry way. Along the way, we create a lot of light, and we create a lot of heat too. I don't know if you've ever touched one of these old-fashioned incandescent light bulbs, but they can feel pretty hot to the touch. So the first law is all about the quantity. Like I said, it stays the same. We've taken energy from the sun and converted it into a bunch of different forms, ultimately into light energy that we can use to light up our bedrooms. The second law of thermodynamics is all about the quality of energy, and it states as energy is transformed, more of it is wasted. Take a look at this picture. I've got a coal-fired power plant right here, and as that water is boiled and the steam is used to turn a turbine to make a generator spin, electricity is created, but this process produces a lot of heat. About 65% of the energy that is harnessed in that coal is lost to the atmosphere in a lower ordered process of heat, right? Meanwhile, 35% enters into these power lines. I don't know if you've ever been underneath a power line before, but the power lines, sometimes they'll crack. You can actually hear it. All along the way, these power lines will lose energy in the form of sound energy, right? Along with a little thermal energy as well. So about 10% is lost to the atmosphere, 90% moves on here from the power lines into our light bulb. And the light bulb, like I described earlier, will produce a lot of light energy and a lot of heat. In fact, about 95% of the energy is lost as heat, and about 5% to light. In addition to the second law being about the energy transforming, more of it is wasted along the way, there's another part to the second law of thermodynamics, and it's all about entropy. Over time, there's this concept called entropy. Over time, there will be an increase in entropy in an isolated system. So the second law also states that in an isolated system, that system will degenerate into a more disordered, more randomized state over time. So we get an increase in entropy. So what does this mean? I like this cartoon here. Take a look at it. This kid here says, I blame entropy. Think about it. Maybe that room that he was living in was a little bit more ordered, a lot less random, and over time there is a tendency for systems to degrade and degenerate into a more disordered state, like this kid's bedroom. I also like this cartoon here. Take a look. This guy sees a sign for the entropy seminar, and it starts out okay. The results of a 5 years steady, right? Over time, in an isolated system, there will become the system would become more disordered, more random. We see this. So I want you to think about this, right? To keep the increase in entropy in our system at a lower value, we can make the system open. And luckily for our Earth is an open system. We have the increasing entropy of the sun is keeping our entropy on Earth at a lower value because we're not an isolated system. So the question then is, how do systems or how do humans increase Earth's entropy? The sun's keeping it lower. How do humans work against the sun? Well, the picture here on the left is telling us how humans can increase the Earth's entropy, how humans can increase the disorder and the randomness of our system. And that's by mining out the Earth's non-renewable resources like coal and then burning them and creating heat. Anytime conversion of a non-renewable resource into energy occurs in our power plants, we are increasing Earth's randomness and entropy. So the question then is, how can humans keep Earth's entropy lower? How can we live more sustainably is another question, right? Well, the picture on the right can help us. If we are using the sun's increasing entropy, like using and harnessing the solar energy that comes from it in solar panels like the ones you see on the screen, or wind turbine energy, or the water movement that is created by the sun in evaporative processes, or photosynthesis even, right? We can live a little bit more sustainably and keep Earth's entropy lower. I hope that you enjoyed this lecture. Move on to the next step, which is to work on those math energy practice problems.